Okay, welcome to lecture 2. I will briefly revise what we did last time. I hope you checked the updates on the blog page. So there is the course outline, there is the link to the notes which are downloadable, there is a link to the video playlist which has only one video in it, and it's quite short also because I didn't do much last time. Today I'll do a lot more. And the last one which I just posted has to do with the lecture by lecture schedule, which tells you roughly what I plan to do in each lecture up to the mid-sem. And in particular on next week, Monday I will teach. So Monday, Tuesday and Thursday. Monday at 2 p.m. Now I have put room 301, but I am not 100% sure that I have that room. So if there's an update, please check before you come on Monday. But it will be at 2. Okay. So actually normally I pause for questions, and in fact I'll start with yeah, why not? We can have any questions you might have from last time. None. Okay, what did we do last time anyway? We just wrote a bunch of scalar field Lagrangians, and they were all pretty simple. And you may be wondering if anything complicated is going to happen. Well, I promise you it will very soon. So the ones we did were real, complex, and vector. And we only did the real vector. And here the symmetry was just phi goes to minus phi. Here the symmetry was phi goes to e to the I theta times phi, which of course includes that one. And here the symmetry is phi goes to phi I goes to O ij phi j, with O transpose O equals the identity matrix. So far so good. And in all of these it's very easy to write the Hamiltonian. You just do pi phi, you calculate pi and then write pi phi dot minus L, and you have the Hamiltonian density. These are also Lagrangian densities. I'll forget to say this word, but okay. Now there is one more obvious one we can add to this, which is complex vector. And here we write we can write it this way. So the phi's are complex fields, but we can also change the notation slightly and write it del mu phi I bar. So our convention will be when the index is barred, it's the same as the star of the field. Okay, and so this becomes m squared phi I bar phi I. And in this case, the symmetry is phi I goes to u ij phi j, where u dagger u equals 1, and this is the unitary group u n, and this is of course O n. Okay, so these are fairly simple family, and I won't go through the details, but in the notes I've explained how to parameterize u, just like we parameterize these O's as exponential of an antisymmetric matrix. The analog here is that u is exponential of I times a Hermitian matrix, and it's pretty obvious. So u, any unitary matrix, is e to the I times last time I don't know what I called it. Let's call it alpha. And alpha dagger is equal to alpha. That makes alpha Hermitian. So the idea is that if this is true, then u dagger is equal to e to the minus I alpha dagger, which is, but because of that relation, it's e to the minus I alpha. And so clearly u dagger u and u dagger are both equal to identity. So it's a standard parameterization. And again, you can write the infinitesimal transformation version of this in terms of alpha. And it's all quite similar, except that in O we use real and antisymmetric, and in matrices, and here we use Hermitian matrices. As you know, Hermitian matrices don't have to be real. In general, they are complex. And we have to use all of them. I mean, one example you know very well is the Pauli matrices. There are 3 of them. They are all Hermitian. 2 are real. 1 is pure imaginary, but they are Hermitian nonetheless. And we need all of them. Hermitian traceless. Sorry, I should have said that. Where did I say that it's Hermitian? And traceless. Well, okay, if it's not traceless, then I get un, and if it is traceless, then I get sun. So I can use both, depending on what I want. Okay, so far so good. Now let's complicate things a little bit more in an interesting way. By the way, I'm assuming that, and I checked, Diptima taught you QFT1 if I'm not mistaken. Yeah, so I checked with him today. So you have done Noether's theorem and all quite thoroughly. So I don't have to go through any of that with you. There's one little interesting point, which is that you can take the complex one and you can just break phi into its real and imaginary parts. So here you have a complex vector, phi I. You can write it as phi r I plus I times phi, let's call it re and im. Okay, and then phi I star obviously is phi re. This is clear. And now if I do this and just plug this into this Lagrangian, maybe with a half, or maybe not with a half, or maybe with a 1 by square root of 2, then I will get basically I can see that this free, I can verify that this free Lagrangian turns into the Lagrangian of the O2n vector model. Basically comes from the fact that the dot product of this with this, phi I star, because of this breakup, will be phi re squared plus phi im squared. Okay, so that's the sum of n components plus another n components, so for total of 2n components, and it's completely invariant under real rotations of all 2n components. Okay, and this is bit misleading. All we've done is taken the free Lagrangian for un vector model and rewritten it as the Lagrangian of the O2n vector model. It's true, it's not a false statement, but when we add interactions, then when I call it the un model, I will be motivated to add interactions which preserve that un symmetry, while if I call it an on model, then I'll add interactions which preserve on symmetry, and they are different. And it will be an exercise for you in the notes to construct an example of that. I've given some details there, and you can try to work out an example how that works. Okay, so un has a natural way of sitting in O2n, but that doesn't mean that every un invariant theory is invariant under O2n, but the free theory is. Okay, free theory is very special because the Lagrangian is completely quadratic in the fields, and in some sense we didn't demand this bigger symmetry, but it just came for free. Okay, please stop me if there are any questions. Okay, now one reason I've introduced these vector models is that vector models have a new parameter, a free parameter, n. Now, of course, if I have any physical system, then n should take some value. Otherwise, I can't identify it with a definite system, right? You probably have heard at least that for the standard model, there's SU3, there's SU2. SU3 governs the strong interactions, SU2 and U1 govern the weak interactions. So there's some choice of n. And actually, it's interesting, nature has decided to choose very small n's in everything we do. We have never in nature encountered SU 257, though we could. I mean, we know how to deal with it. It's just part of the family of SUN groups, but it's not like we know any system which really uses that. But a very beautiful fact which was discovered many decades ago, maybe half a century ago, by Gerard et Hooft, who won the Nobel Prize for renormalization of Yang-Mills theory, you might know, noticed that taking n to infinity simplifies theories and gives a new calculational tool, which is different from perturbation theory. So perturbation theory is an expansion in the coupling, for example, E or lambda, whatever we want to call the coupling. In electrodynamics, it's called E, right? You have a coupling E, A mu, psi bar, gamma mu, psi, for example, in quantum electrodynamics. So perturbation theory is expansion in that, but the 't Hooft expansion is a different one, and it's an expansion in 1 over n, in powers of 1 over n. Now, since n never gets beyond 3 in nature, you would think this is pretty silly. What does it mean to have an expansion in powers of 1 by 3? Well, surprise, surprise, you thought the expansion in E is good, right? Okay. What's the value of E in dimensionless units, where h bar and c are both set to 1?
E square root of 1 by square root of 137.
Thank you. So, exactly right. So, E squared by 4 pi is 1 over 137. This is the fine structure constant. Okay, so let's solve for E. What is it? It's about 1 by E squared. It's 1 by 11. That's about 0.9. Sorry, did I do something? 12. Yes, 1 by 11. And therefore, E is about 1 by 3 point something. Yeah? Pleasant surprise. If you had first been told we are going to develop a theory of quantum electrodynamics which will be an expansion in powers of 1 by 3, you would say it's crazy, because if the first correction is order 1 by 3, next correction is order 1 by 9. But the discrepancy between, so what we are losing is about 30% of what we are keeping. Okay, and that's not very good. That means we are making 30% error. Why are we not doing that? Because this isn't this is the naive expansion parameter. It's what is there in the Lagrangian, but it's not the actual one that occurs when we do calculations. The one that occurs in calculations is that. And without setting up the calculation, we wouldn't have realized that instead of E, we get E squared. So QED is a power series in E squared and not E. All right. And also one wouldn't have realized that 4 pi necessarily comes with E squared at every order, which is a fact. This fact is why we define alpha. Otherwise, we would have no motivation to define alpha. And once alpha is the expansion parameter, then the first term is of order 1 by 137. That's the first correction to anything. And the next correction is 1 by 137 squared. Now it sounds much, much better. So 1 by n is not such an absurd idea. In fact, there are theories where the expansion is really in 1 by n squared. And then there are other factors. And so we can learn things. Whether we do 1 by n expansion in this course, I don't know, but it has become a very central ingredient of how we think about quantum field theory. It's been around for half a century nearly. I think 't Hooft did this work in 70s or 80s, I think 70s even. But it has become even more prominent in recent years. It has taught us a lot of things we otherwise did not know. So just to tell you why I introduced vector models at all. Okay, good. Now the next class of models also have a parameter, and these are called matrix models. And again, they come in different varieties. So now we'll take this phi, the scalar field, and do this, write it this way to represent that it's a matrix. In the notes it will be in boldface, and its components will be labeled phi ij, and it will be an n cross n matrix. And it's common to impose some constraint on what kind of matrix. Okay, so usually we ask it to be something like again orthogonal or Hermitian or sometimes unitary matrix. So here we'll choose it to be a Hermitian and traceless matrix. So it's still, we are still doing scalar field theory. We've simply chosen our field to be a complex but Hermitian and traceless matrix. And now the Lagrangian density we can write for this matrix would be del mu phi star. Okay, so del mu phi, well, since it's Hermitian, probably don't even need to put the star. Actually, I don't need to put the star. I think I should have not put it. What I need to do is to contract the indices, and the way I do it is that this index is identified with this and summed over n values, and then this with this and also summed over n values. And there's a very nice shorthand for this kind of product of matrices. What is it? Trace of the square. So it's half trace. Let's put the trace outside everything. Half del mu phi del mu phi. Okay, and now we can write a mass term. Here it would be minus m squared by 2 phi ij phi ji. And in this notation, it's just minus, so I can take minus m squared by 2 phi matrix squared. Okay. So it's a bit like the vector model in that the field has some indices, so there are many scalar fields. So I promised you that life with more scalar fields is more fun than life with one scalar field. And this is an example. But why is it interesting? Well, as usual, these things are interesting depending on what symmetry they have. And in this case, the symmetry is again un, and it acts as follows. Phi, the matrix, goes to u phi u inverse or u dagger. U dagger and u inverse are the same thing. Okay, so this u also is a matrix. I'll get tired of putting these things, but this is the transformation. Now what happens in this one, I get, so these are constant matrices, these u's. We are only looking at global symmetries for now. And so there's a u here and a u dagger here, but this guy gets a u on the left which cancels the u dagger, and it gets a u dagger on the right, but then it's in a trace, and so u dagger comes around on the other side and it cancels the u. So a trace is invariant under this sort of transformation, and so the symmetry of this is un. Okay. Now there's a little subtlety. As you know, un has a part which is u1 and a part which is sun. Okay. Sun are the ones of determinant 1 and u1 are the phase. It's just a matrix which is identity but with an overall phase. Now what happens if I use the u1 part of this in this transformation? I get a phase here and I get the opposite phase here, proportional to identity matrix. But then this can already come through and it doesn't do anything. Two phases just cancel. Okay, so the phase part is trivial. acts trivially. So really the symmetry of this model is SUN. Okay, and again one can consider large n and think of large n expansions, and it has a different flavor. Why? Because how many degrees of freedom does a phi have? A single matrix n cross n Hermitian has of order n squared. Actually it has precisely n squared components. Okay, maybe -1 for traceless, but it's basically n squared. Because the real part is well, you can work it out. I won't try to do that here. So the field has order n squared components. And that's qualitatively different from the vector model where the field had order n components. So the way these two kinds of fields behave in large n expansion will be different. Now that I'm discussing this mentioning this large n so many times, I'm sure that I will find time to dedicate at least 1 or 2 lectures to it, but not right now. Let's get a little further ahead in the course, because right now we are doing classical field theory. So there isn't any kind of expansion. We're just writing a Lagrangian and its equations of motion, finding its symmetries and stopping there. Okay. So that's, I think, what I wanted to say about UN. Okay. 1 or 2 simplifying things. Instead of writing this as a matrix, there is a way to write it a bit more like a vector. So introduce generators TA, these are also matrices, A equals 1 up to n squared minus 1, and that's the dimension of the group SUN. So these are the generators of the algebra. That means by taking linear combinations of them, I get any element of the algebra, and by exponentiating it, I get the group. But right now, we're taking our scalar field to be valued in the algebra, not the group. And so it has to be a linear combination of these. So now we can expand phi, the matrix, as summation phi A, which are again fields, times 2A, summed over A from 1 to n squared minus 1. Okay, we can always make such an expansion, and we can also find out the phi a's if we are given the matrix by inverting this. That's done by noticing that the generators are normalized, so the t's are normalized. If something is a generator of an algebra, then any number times that will also generate an algebra with a different normalization. So we better choose one, and the standard normalization is T A trace of T A T B. This is in the these are in the fundamental representation. So they are n squared, n cross n matrices, and A goes over this, and we choose this to be a half delta AB. It's easy to show that one can choose these T's such that trace of TA, TB is proportional to delta AB by some scalings of the algebra, and then the half I can just choose. I can also choose 2 or 10 or anything I feel like. If you, since you're familiar with Pauli matrices, you know that the T's for SU2 in the fundamental representation are half the Pauli matrix, and you can verify that trace of half sigma A, half sigma B is exactly that. Okay, so it's consistent with SU2, but we choose this half for all SUN once and for all. In that case, it follows from this expansion that phi A is the trace of the matrix phi, the matrix TA, these two matrices multiplied, times 2.
So,
yes?
So these generators are the generators of the group, or are they something else?
So we always write generators for an algebra, and the exponential of the algebra, roughly speaking, is the group.
Yeah.
Okay. So you can go through that in more detail later. If you want, I can give an extra lecture on it. If you want, you can ask me to do that, or you can just come and discuss it with me. But T's are the generators of the algebra. the basic idea is that a Lie group is, so a Lie algebra is relatively simpler in one sense, in that it's a linear space like any algebra. In an algebra, I can take linear combinations of things and they're still in the same algebra. In a group, if I can't take linear combinations, I can only multiply things, okay? And precisely in the sense that addition is a simpler operation than multiplication, Lie algebras become simpler than groups. If we take the exponential of generators of the algebra, then we get an element of the group, and now adding the algebra up there is like multiplying the exponents, okay? Of course, up to some commutation issues, and those commutation issues are exactly what capture the details of the algebra. It's a very broad thing I've just said, but well, ask your group theory teacher, who is going to come back soon, I think. Srijit is going to teach you people group theory. Some of you at least are taking it, or all of you? Group theory in physics, I mean.
We have already taken the course.
You've already taken the course last year, is it?
Yes. Some have taken, some are taken.
Ah, is it offered in alternate years?
No, sir, alternate
It's offered in
semesters.
sixth and eighth
Semester.
Sixth and eighth semester. Oh, some of you took it in sixth and some. Okay, it's offered every year, but you can take it in sixth, right? So if you have taken it, all the better. Then all of this should be familiar to you. But if not, go back to the book or come and discuss it. Good. Okay. Now there are a few nice relations. I told you that I can parameterize any element of the group as an exponential of the generators. So I write element of the group in the fundamental representation is exponential of generator times some parameters. These are the parameters of the group. In the case of SU2, there are 3 angles, which you know, which are familiar, rotation angles. But in a general SUN, there are n squared minus 1 of them, and they are just some parameters. They are also angles, though. Because of the I, these things have periodicities. So they are not unbounded, they are also angles. Now, if I do this, then I can see that phi going to U, phi U dagger must translate into a statement about the infinitesimal version. So if I take theta very small, then this is 1 plus, so 1 here means delta ij plus I theta a t a ij for small theta. Okay, and from this I can calculate delta of the matrix field phi under an infinitesimal transformation. Now what happens is that here I get an exponential like that, so I get this plus I this. Here I get this minus I that, because it's the dagger of the previous one. These are Hermitian, only I changes sign. Okay, but in one case I got the t on the left from this one, and in this case I got the t on the right, and with a minus sign. So in the end I get a commutator of ta with phi times the parameter theta a times I. Okay, so this is a commutator t times phi minus phi times t, and this is interesting. You can see from this visually, but you could have also seen it from here, that if the specific matrix valued field happened to be proportional to identity matrix, then of course it didn't transform at all. The transformation became trivial. And here we see that by the fact that the identity matrix simply commutes with the t's. So that's the infinitesimal version. And you can also use this to find out the infinitesimal variation of the phi a, where phi a are the components. Okay, and then what will happen is that since you'll expand phi in its components, it will be phi b tb, to give a new index, then you'll find a commutator of TA with TB, and you know that is I FABC TC. So therefore delta phi A will actually be FABC theta B phi C. And in this relation there's no I, and that's important because phi, remember, these are the components, these are real. This field is Hermitian. A Hermitian field can be expanded on a basis of Hermitian matrices with real components. If I put anything complex here, that won't be Hermitian anymore. So these components are real. So I can either think of phi as a matrix, which is Hermitian, or as components which are real. How many components are there? N squared minus 1. And the components change by the structure constant times the parameter and the field. This thing will keep cropping up in future in this course because it also is an important relation in Yang-Mills theory, and so is this. So it's good to introduce it now, where we don't have any complication of gauge fields, gauge symmetry, none of that. We just have scalar fields, and this is how their symmetries look.
Excuse me, sir.
Yes.
Can you please explain what FABC is?
So in a Lie algebra, so you have you done the group theory course? Maybe not. You're going to do it now? Okay, sorry. Okay, thank you. So let's do that here. So if I have a Lie algebra and I have some matrices which define the algebra in some representation, which here is the fundamental, but actually in any representation, then the Lie algebra comes with a bracket which is a kind of inner product, but it's an anti-symmetric one because it's a commutator, so it's odd under exchange of A with B. But under this bracket, we should get back an element of the algebra. So this must be a linear combination of the T's again. So I put a third T here, Tc. Now the linear combination is parameterized by some numbers, pure numbers, which depend on A and B as well as C. And so I call that linear combination FABC, and I put an I because my T's were Hermitian. And if I take the dagger of this commutator, it changes sign because of it exchanges this, dagger of product of two matrices, the order goes reverse. So this changes sign, but this won't change sign, so I put the I. Okay, and other than that, FABC are real numbers. They are characteristic of the particular Lie algebra. So SU2 has some FABCs, SU3 has its FABCs, and every Lie algebra has its FABCs. And for SU2, it's just epsilon ABC, which is the easiest possible structure constant anyone could ask for. But for all others, it's more complicated. So these are called structure constants. They do depend on the basis T that I choose, and they will depend on the normalization of that basis and everything, but up to all that, they are unique. And one of the key discoveries in theories of these so-called compact semi-simple or simple Lie algebras was exactly how to calculate the structure constants. Then you really know that you have the algebra. Okay, so we've gone a long way with free field theory, but there's not so much. Actually, it's surprising that you can say a lot of things about free field theory, but there are not so many things we can say about classical field theory. We are pretty much done, and so now we need to. So we need to go in one of two directions. Either we quantize this or we add some interactions. So let's first add the interactions, and the quantum part is coming later in the course. So we now add interactions to all of these models. And it turns out, surprisingly, there's more than one way to add interactions. So you will know at least one of the ways. So supposing I start with the simplest case, del mu phi minus m squared phi squared, then I simply can add a potential, P of phi. Okay, this I'm sure you have studied, and probably you have encountered the case where V of phi is phi to the fourth. One comment is that sometimes we call this whole thing V of phi and we just take the mass term into it. It's up to us. We may want to keep it separate or we may want to take it in. That's matter of convention, but this is how to introduce an interaction via potential. And you know already that if I go to the Hamiltonian, this will appear as plus V in the Hamiltonian, and it will be like a potential energy term. It will tell the field classically where to sit. So the equation of motion will depend on the derivative of V, and then to minimize it, to find solutions of it, phi may like to sit at the bottom of some potential, just like a particle does in classical mechanics. Okay. Good. Now let's look at some examples. So it should be more than quadratic, because if it's quadratic, it can only be this or this. Okay, at least under my assumptions. and then we have already accounted for them, so we should be at least cubic in phi. Okay. So an example would be lambda 3 by 3 factorial phi cubed. Another example would be lambda. I'm giving lambda the name 3 or 4 to show you that it multiplies the third or fourth power. So these are examples of V, and we could also add them, for example. Okay. So we can have V doesn't have to contain any one power, it can contain lots of things. And what it contains will tell you something about the symmetries of the theory. For example, if I only have this phi fourth, then the phi goes to minus phi symmetry is preserved. But if I have this, then it's not preserved. If I have both of them, then it's also not preserved. Okay, but actually by shifting phi, I'll be able to again get the symmetry back, because basically it's a cubic plus a quartic is again a quartic after I shift phi. This is something you can work out for yourself. There's another thing which can go wrong. If I have only phi cubed, well, what does it look like? It looks something like this. And you see that this is phi, this is V, and this is what the phi cubed curve looks like. And this isn't good, because it means that classically the field will roll down to minus infinity. So, and it means that the Hamiltonian will be unbounded below, because the potential can take a value as negative as I want by phi going to minus infinity. Hamiltonians with unbounded potential are quite scary, because most physical processes don't make sense in that situation, because right, everything tries to minimize energy and there's no minimum of energy in such situations. So phi cubed by itself isn't very good idea, but if you add these, then this one wins for large phi, even large negative phi, and so this curve comes back up. So as long as the last term in this polynomial is of an even power, then you're good. So these are all things you need to keep in mind. Now there's an exceptional case which almost one would have felt silly to discuss, except that it happens to underlie all of known physics, which is the case where I take this and I perversely change the sign of the mass term. So I write half del mu phi plus m squared by 2 phi squared minus, let's say as an example, lambda fourth phi fourth. Okay. Now formally this looks like m squared being negative or m being pure imaginary. Okay. So in order to understand it better, we should sketch what this curve looks like. So at phi equals 0, it's certainly 0. So what I'm going to sketch is V of phi, and now I'm combining this and this together into V of phi, because the field will experience the sum of them. So V of phi is minus m squared by 2 phi squared and plus lambda phi fourth. So the first thing to realize is that when phi is very large, this term is negligible and this is positive. So the potential is not unbounded below. Okay. On the other hand, when phi is very small, then this is negligible and this is negative. And so you easily see that the shape is like that. It has a double well like that. Okay. With a minimum here. And it's very confusing at first what it means to have m squared of the wrong sign. And formally the statement is that this theory has a tachyon. Why tachyon? Because normally the mass of the particle is given by the quadratic term in the potential, in a potential which is like that. If the quadratic term is upside down, then the mass doesn't look very sensible. And that's exactly the same statement as saying that if I put the field to take this value and I just give it a little kick, it will roll down. So it's an unstable point. This obviously, it's not a minimum, it's a maximum. And a maximum is an unstable point of a potential. So that's the physics. And we'll do it in detail, not today, but the resolution of having an unstable point is that we don't study the theory about the unstable point. Instead, we define perturbation theory about a stable point. As simple as that. The interesting thing is that a lot of stuff happens around the stable point that we probably wouldn't have guessed. and it kept people busy in the early 1960s when they started to understand this phenomenon. It's called spontaneous symmetry breaking, and I'll dedicate a significant time to it. But right now, all we are saying is that's a possible potential. So our rule is, as long as the last term in the potential is has a positive even power and a positive coefficient, we are good. We don't really, all the terms before that can be positive, negative, have any sign they feel like, but the physics may be different, but they're all legal. Okay, good.
Sir,
Yes.
so when you have a case like this,
Hmm.
you said that you usually associate the mass of that
Hmm.
field with the quadratic
Hmm.
power, the coefficient of the quadratic power. So in such a case, do we associate the mass when we consider that stable point, and is that the mass of
Yes,
the
yes, exactly. So what we'll be doing is shifting phi by a constant so that phi takes the value 0 here rather than there. And then we'll look at the curvature here, and the quadratic term around this point will tell me the actual mass of the field. And surprisingly, it turns out to be square root of 2 times this one in simple models, but that's a detail, we can do it. We will do the calculation. So, but it's not, in any case, the important point is that there is a particle and it has a positive mass. Okay, let's be a little more careful. Yeah, no, I think I didn't say anything wrong. There is a particle and it has a positive mass. When phi is complex, I can do the same things, but then the resulting spectrum is more subtle, and that's also important. What will I do when phi is complex? Well, as usual, I'll drop the 2 and I'll put a star here, and I'll have V of phi and phi star. Okay, sorry for overwriting everything, just easier for me. So in the complex case, this is what will happen. Now, the potential is a function of these, and the theory has, remember, now a U1 invariance, which was not there before. And it's a good idea to keep the potential having the same symmetry, namely V depends on the product phi star, or not on separately phi and phi star. Okay. Now, that's not absolutely necessary, so you can write V's which depend only on phi and phi star in a way that violates U1 symmetry. And there are some exercises about that in the notes. But the sensible one would be, the only one which really preserves U1 is V of phi star. And now I can again take this to be plus, and what I'll get is like a double well, but it's a complex field, remember. So I plot real of phi here, imaginary into the board, and V, the potential, this way. And now I have to just take this, and in my mind I have to rotate it. So it's like a bowl with a little bump in the middle. Depending on your cultural preferences, this is sometimes called a Mexican hat, where the Mexican hat has that kind of form. Some people call it a whiskey bottle. I would never do such a thing, but I'm sure you know why, right? Some bottles, when they are blown, they develop a bump in the middle which comes up. I think I can see some people nodding. Yeah. Okay. So that potential, and it's the same problem. Over here the mass seems imaginary, but actually we should go there. This is just to prepare you for what we'll do later. Good.
Sir,
Yeah.
like based on the last question,
Yeah.
so here how do you associate a mass at the stable points? Like because it's now in 2D,
Yeah.
like different directions might have different like.
And in fact, one of the directions has the zero mass, which is the direction that goes along this base, and that's called the Goldstone boson, and you have just discovered Goldstone's theorem. This is Goldstone's theorem in its simplest form. So we'll come to it. And interestingly, Goldstone phenomenon, which is exactly this model, it's not precisely realized in particle physics in this form, but it is realized in condensed matter physics in this form, and very often in condensed matter people talk of Goldstone modes. And what are they? They are massless modes that arise because of these kind of potentials. Good. Gapless modes in their language. Okay. Now, in the remaining time, we still have a lot, by the way. We have not still scratched the surface of scalar field theories. We still have a lot more of them to do. So now we should add interactions to our vector model. So yes,
One question, like,
yeah. Tell me.
why do we associate that coefficient with the mass of the particle exactly?
Well, by definition, because if somebody told you that the Lagrangian is this term minus v of phi, then you would have to pull out the phi squared term and it's the same reason why this term is associated with the mass, right? If I have a v of phi which I haven't told you what it is, then you'll do a Taylor expansion. You can choose that its value at phi equals 0 and its first derivative vanish, and then if they don't, you would have some problems, and then it starts with second derivative. So it's just a set of Taylor coefficients a n phi to the n equals 2 to infinity. When I have a potential like this, the first term, the phi squared term, is what tells me the mass. That's, if you don't agree with that, then why do you agree that this term is the mass term of a free theory? The same reason, right? It's just we take v, we expand it, and we pick out the quadratic term, say that's the mass term, and then cubic onwards is the, so to say, true potential, the one which has interactions in it. So, of course, it can be answered by saying that in this form, the Klein-Gordon equation is box plus m squared, and then you can work out the free particle solutions and see that they have that mass. Another way of saying it is that the quadratic term in V is the same as the linear term in the equation of motion. And the wave equation is the one satisfied by the linear part. Everything else is non-linearities. Yeah. Okay, so what potential should we add here? So again, we have a similar situation. We would like to add a potential which is invariant under ON, which was the symmetry group of this part. Okay, and there's an easy way to do it, which is that V depends only on the product phi I summed over I. If it depends only on that, then everything sort of goes through the same. In fact, I can even then easily think of a Mexican hat like potential in n dimensions. It's very difficult to draw, but I can do it. In fact, the example I gave you before was just this with I equals 2. Single complex scalar field is the same as the vector model with only two components, which are the real and imaginary parts of that field. It's an exercise. Okay, so this is allowed, of course. So this preserves ON. But now we are led to ask the question, what else could preserve ON symmetry? This is my alarm. So that not to go over time, so I have 5 more minutes and then we'll stop. So what else can preserve ON symmetry? Well, for that we need to think about how we reach this conclusion, and actually phi I is the same as delta ij phi j summed over both I and j, and it happens that delta ij is an invariant of the group ON. Okay, that's the same statement as saying that if you act on this by O and O transpose, you get it back, which is the defining relation of ON. O transpose is 1. This is 1 as a matrix. Okay, this is an invariant of ON. It's also called an isotropic tensor. So invariant tensor or isotropic tensor of ON. Now ON fortunately doesn't have many more invariant tensors. Actually it has only one more, and that one is epsilon I1 I2 up to In, the totally antisymmetric symbol with n indices. Okay, and as I'm sure you know how to figure this out, starting with epsilon ijk in 3 dimensions. There's even an epsilon ij in 2 dimensions. It's just the thing where the values 1, 2, 3, 4 dot dot up to n, that thing is +1, and then any permutation of it you have to just take total antisymmetry into account. So totally antisymmetric. So this is also invariant of ON. And so you might try to guess an interaction like epsilon I1 up to In phi I1 to phi In. This would be invariant under ON because this is invariant. Okay, if each of these transforms under ON, then all those O matrices can be made to multiply this, and there they give this back. That's the statement that it's an invariant tensor, and we get it back. So it is an ON invariant, but unfortunately it's a very uninteresting one. It's 0. Why is it 0? Because if I interchange I1 with I2, this picks up a minus sign, but phi I1 and phi I2 can just be moved around. They're just classical fields, so they commute with each other. So then it's 0. So this is not much fun. But you could have a theory, this leads us to more generalizations, have a theory where your phi has an upper index I and a lower index A, and I goes from 1 to n and A goes from 1 to m. But we give them different names. We say this is the vector index and these are ON vectors under this, but this one we'll call a species index. Just give it a different name. Okay. Now you see, if the species index has, so there are, it's like having multiple species of particle, each of which is a multiplet of ON. And now of course I can make such invariants by simply putting a A1 up to AN here, and it will not be 0 as long as the range of values of these A's is possible values is larger than the range of values of these. So that m is greater than or equal to n, then I can do this. So I can actually get an invariant of ON if I have multiple species, each of which is an ON vector. Okay. And the last thing I want to say before I close is what happens for SUN, where it's a similar story, but it's a little different in an interesting way. So of course, the SUN vector model is just this, but I should put stars here, and then I have to have V of phi I and phi I star. Now SUN has an invariant identity, but we call it delta ij bar. This is very important because if I multiply this with phi I and phi j bar, remember this was phi star I, then this should be invariant. Okay, if I had called it delta ij, then I would multiply it with phi I and phi j, both of which are complex, and I don't get an invariant. Okay. Now you're all looking very puzzled, but you know this. In a meson, do you have two quarks or you have a quark and an anti-quark? Why? Just what I said. If delta ij was the invariant, I would have a two quark invariant. Okay, because phi's would be quarks and phi bars would be anti-quarks. Okay, there are scalars here, they are not fermions, but that doesn't affect the group theory at all. Group theory doesn't care much about that. That's why my lecture on fermions will be a copy of, and we'll just have the same situations as here with a few minor changes, because these are an extra index which has nothing to do with the bosonic, fermionic or space-time behavior of the field. Okay, so there's delta ij bar, that's an invariant, but there's another invariant which is f I j k, and with f I can make an antisymmetric combination phi I, phi j, phi k, and it has the same problem as this one, namely if I don't have species, then I get 0. This also, if I do this, Fijk is the structure constant, is totally antisymmetric. If I don't have species, I get 0. But if I have some species, then I can get an invariant. And well, what invariant does nature make out of this construction? Protons, neutrons, nucleons, they have 3 quarks. No anti-quarks, only 3 quarks. So 3 quarks combined into an SU3 color invariant by this. I don't expect you to know SU3 color. We have to actually develop it, both me and Arun, in our separate courses. But you must have read about it and you know enough to appreciate that this invariant is important. So therefore, moral of the story is that for V to be invariant, it should depend on either combinations like that or combinations like that, wherever they exist. And then your theory will have SUN invariants. And we still have a fair number of scalar field theories to go for next time. Any more questions? Any questions? Yeah.
So I didn't understand what exactly the species index are doing.
It just so we have fields, right? So we can have any number of fields. Species. I called it a species index. So I don't know. You know that electron and muon are both different particles. So the field of an electron and the field of a muon, I could call it phi 1 and phi 2. Then the label 1 and 2 would label electron and muon, but each of them would have a spin up and a spin down orientation, as well as similar for its antiparticle. So each field would have 4 components, that's a spinner, and then I have 2 of them with a species index. These are just words. You could also call the spin up and spin down state as 2 different particles if you felt like. So what we call as same and different particles is words, and every field can have lots of indices and labels. And some of them we say, oh, it's a different particle because maybe it has a different mass. Some of them we say, no, it's the same particle in a different state. So that's how the species index would work. So if I had different species here, then they could have different masses, each of which would be separately ON invariant. The first species would have phi I as its mass term. Second species would have phi I, but with a different m in front of it. So I don't need to have all of them of the same mass. So that would make them species. Okay, more next time. Thank you.